Okay. All right, sorry for a little delay here, guys. I kind of ran over in my previous class. And I'll try not to do that to you as well, but we're hitting some hard material here, so. All right, so how's everybody doing? Staying alive, staying active. By the way, what are you guys doing to not go crazy when you're confined to your homes for such long periods of time? What's your stress relief? Is it just math, or is that only me?
Yeah, I'm just studying.
Don't need stress relief. Life hasn't changed.
Yeah, actually for me, life hasn't changed very much, except that I'm annoying the rest of my family more by making a lot of noise for several hours a day with Zoom meetings. So. All right, let's get this started today. So a few things here. First, let's clarify. You have a test coming up. Your test is going to be on Friday, by which I mean it will start on Thursday, sometime in the middle of the day, Thursday. I'll email you and I'll put something up on Canvas and on the course webpage. And what I will do is I'll put links to an exam that I'll post for you. And that exam is going to come in two parts. There will be a quest portion that will open up for you, and then some free response, probably just a couple of free response questions. You will have a total of like 24 hours to get it done, and you can use all of that time to work on your free response questions. I'm going to try, I'm going to see if I can figure out how to get Quest to just like give you 1 hour to work on the Quest questions so that you don't labor over those things too much. You should be able to start whenever you want to start, if I can arrange it, and then just get that done within an hour. They'll be pretty much just like the homework questions, in spirit anyway, except since it's an exam, you don't get multiple attempts. You just, whatever answer you have when you're done, that's the answer that'll stick. I'm going to have to figure out, there is a way on Quest for me to, on Canvas, for me to make this as an assignment for you. So something that you will have to scan and then upload it to Canvas. If you have a scanner, that scanning is easy. If you don't, there are some apps that you can put on your phone that kind of just let you wave your phone as a camera. It waves over your paper and it turns that into a PDF or something. You can, if you can't figure out how to make it work on Canvas, you can email it to me. And if you're stuck with everything else and you can't figure out a way to scan it, then you'll have to find a way to kind of type in your answer, and you can just send it as a text message, as an email to me, just in ordinary text. If you think that this is not working for you, you can't make any of those systems work, then send me an email or something, and I'll try to help you, and we'll deal with it. But let me not stress over that too much, because I still have to figure out what Quest can do for us. The other thing is about the content. So the content will include everything we've done since the last exam, which is pretty much just integration, including all of the change of variable types of problems that we've had. And now these different types of integrals, we've done the path integrals and some surface integrals, which we'll do more of today. And I would also like to introduce you to the line integrals, which are the ones that involve vector fields. And I'll say something about that in a minute. So the test should coincide with the material that you're doing up through the current homework set. So you should make sure that by Wednesday night or Thursday morning, you know how to do all the types of problems that are on the current homework. So with that in mind, are there questions that you want to ask me about the test?
Will there be vector curl and like vector or like divergence?
Yes, I guess. Did we have questions about that on the last test? I actually don't remember. That's about where we left off on the last exam, and I don't remember if I asked you questions about that.
We didn't have questions on that.
Yeah, I didn't think so. Well, you're going to discover today as we move into these line integrals, this is kind of the reason why we wanted you to know something about vector fields earlier, is so that when we got to the stuff we're doing now on line integrals, I'll show you that we're going to be needing the vector fields. Specifically, what did we do with vector fields when we had them before we got around to integration? The answer is really all we did was to calculate a few types of what you could call derivatives. So there were all those different types of things that involved partial derivatives. And yes, those are the divergence and the curl and the gradient. We also had some theorems that explained how those types of differentiation kind of linked together. So we had a few theorems that said, basically they said when you do this and then you do that, you end up with a zero. So things like if you take the curl of something, then you end up with a zero. And there were some things that were all basically types of product rule. Frankly, I don't want you to memorize any of those things, but they are kind of important. I will point out that this is just going to have to be an open book exam. So if you can just find the sections in the book that do talk about the divergence and the curl and whatnot, you might as well just bookmark those things. I mean, mark them in your notes somehow, and then you can refer to them while you're taking the test. I'm not trying to say that they're not important, but really that's not quite the focus of what we've been doing since the last exam. And I know that in practice, you guys, if I asked you about this stuff 10 years later, you won't remember exactly the formula for the curl anyway, but you will know that it was something important that had to do with vector fields, I hope. And then you'll know how to look it up and how to interpret it when you get there. So that's a long way of answering your questions. Yes, I might put something about the curl and whatnot on there, but I wouldn't stress it too much, but do know where it is in the book so you can refer to it if you need it. Somebody else had a question about the exam? I don't see a hand up. All right, let me ask you then about the homework, because that also overlaps with this, this material. Yes, Yangzhu.
Sir, can you go over the last question in the homework?
Yes, if you remind me what it was. Or actually, I think maybe I have it up here on my browser. The very last question. Is this the one that says, evaluate the integral of a surface where S is the portion of the plane that lies above the unit disk? Is that the one you're asking about?
Yes.
Okay. Let me just ask you what are the formulas that you have, because for me, I'll write down the formulas and then I'll turn the camera around. These are the formulas that they give me. My wife is going out to run. Some of us are trying to stay sane by getting out and running. I had a 30-mile bike ride yesterday. That was fun. X plus 2y plus 2z equals 0, and x squared plus y squared is less than or equal to 1. All right, here's some formulas. Do these match yours? And if not, how are yours different? Oopsie, let's get the right thing up here. How do those look compared to the ones that you had?
Yes, they are identical.
Oh, perfect. All right. Oopsie. Well, as it happens, I was going to do a very similar example with you guys. So I'll sort of recycle the picture even though the formulas are not quite right. What I was going to do, if nobody asked any questions, was I was going to run through this surface integral with you. So here you see the same sort of thing that you were given in the problem, Somebody asks you to compute the integral of a function of 3 variables over some surface that floats in 3-dimensional space. As always, you chop that up into pieces. You multiply the values of f times the size of the pieces. And that's why I wrote dA here, was a reminder that size means area. I did notice that in the Quest, they're using capital S there, DS. I don't know why. That doesn't stand for anything that I know. S for surface, maybe? I don't know. But I would write it as dA, and that's just the kind of thing that I had here. Now, if you just wanted the area, that's what I was going to have you guys work on. The area comes from integrating the constant function 1 over a set. And then this will, no matter what the set S is, this will always give you the area. But I'll do their computations because they're pretty similar. You have a cylinder. The set of points where x squared plus y squared is equal to 1 would be a cylinder that's wrapped around the z-axis, right? So here's one equation in the 3 variables. 3 minus 1 is 2, which means that you have a 2-dimensional set, i.e. a surface. If you want to stay on the inside of the cylinder, that's where you want x squared plus y squared to be less than or equal to 1. But you are supposed to be actually on the plane. If you, again, here's one equation in 3 unknowns. 3 minus 1 is 2. This is again a surface. I hope you recognize that that kind of equation describes a plane. There's a plane intersecting this cylinder. Those 2 equations, well, these, if I turn that into an equation, there would be 2 equations in 3 unknowns. 3 minus 2 is 1. A 1-dimensional set is a curve, and that curve will actually be an ellipse that's floating around in space. But we want to have the region that's on the interior of that ellipse. We want to have this part exactly equal to 0, but this part be less than or equal to 1. So you're on the inside of the cylinder and on the plane, and that's the picture you should have. It's not, shouldn't be quite lined up with the axes the way I did here, but you got that? So you're going to take this elliptical disc, split it up into little pieces, multiply the area of each piece times the value of this function somewhere on that piece. Now, how do you compute an integral over a surface? Step 1 is always going to be that you have to somehow parameterize that surface, that chunk of 3-dimensional space. Well, it's not really a chunk. It's a flattish chunk. So I have a couple of options for you for how you can parameterize that floating elliptical disc. So one option would be to just say, look, this set that this plane that you're describing is the graph of some function of 3 variables. You could write this as z is equal to minus a half an x minus a y, right? So the plane is then the graph of a function of 2 variables. And there's a cheat that you can use when you need to parameterize the graph of a function. If you need to parameterize the graph of a function of 1 variable, you know what we've done. We've just let x be the same as t, and then y is whatever function of t you need to be on the graph. When it's the graph of a function of 2 variables, in a similar way, you just let x be equal to the first parameter and y is equal to the second parameter. You need 2 parameters to parameterize a surface. That's what it means to call a surface 2-dimensional. It's parameterized with 2 parameters. So the first 2 variables are just, the parameterization is you just let x and u be synonyms and y and v are synonyms. And then the third one is just got to be whatever the formula says it has to be. So in our case, this would be minus 1/2 times u minus v. And then that expresses each of x, y, and z in terms of the 2 parameters u and v. So you would have a function, capital T, that goes from the UV plane, and it maps us into 3-dimensional space. That's supposed to be an illustration of an elliptical disc floating around in 3-dimensional space. Sorry, my pictures are pretty cheesy. Okay, so I apologize, I had a different example lined up for you guys, but I'll try to adapt it as we go here. So here's my parameterization. T will take the 2 parameters u and v and spits out just u for the first, v for the second, and it'll have to be this formula involving u and v for the third. And after you've got your parameterization, then you need to rewrite your integral by changing all three of these things to just refer to u's and v's. So the first step is to ask, well, what combination of u's and v's do you need to end up on that floating elliptical disk? And, well, it's kind of easy because, like I said, in our parameterization, we're using u as a synonym for x and v as a synonym for y. So the portion of the UV plane that we need is the same as the portion of the XY plane that you get by just looking at the X and Y coordinates of the points that are on that disk. If all you care about is the X and the Y coordinates of these points, oops, sorry, I'm pointing. If you only care about the X and the Y coordinates of these points that are floating in free space, just smash everything down to the XY plane. Straight down. You just drop a perpendicular to the XY plane from every one of these points, and they'll take you down to some other point that just lies in the disk. There's the unit disk that's at the center of this ellipse, at the center of this cylinder, and you've intersected it with this slanty plane, but you guys have the camera angle right now. You just take every point on that rises above the circle. And then take every one of these points that's up here somewhere above the XY plane, just drop it straight down. I can't do it. I can't match the camera angle. Anyway, what I hope you realize is that you're going to get all the points that are in the unit disk, centered at the origin. All the points where x squared plus y squared is less than or equal to 1. So the portion of the UV plane that you need will be this disk centered at the origin. In our example that you just asked about, the radius will be 1. And this transformation capital T is going to turn all of those into the points in three-dimensional space. Literally what it's going to do is take each point on the UV plane that you see on your screen, and it will just raise it up this many units in the z direction, the third direction. That's exactly where you'll be in the x direction. That's where you'll be in the y direction, and this tells you how high to go up in the z direction. So that's the first step, is to rewrite your region of integration to be a region in the UV plane, and this is the answer of that. The next step is to take the function that you're integrating and compose it with t. In other words, to replace every x with this, every y with that, and every z with that. So for us, the function we're integrating is now going to be, here's z squared, here's x, and here's y. So that's the function that we have to integrate. Well, almost there. That's what our integrand has become. We have just expressed it. I shouldn't say that's f. That's really f composed with t. You've substituted in these expressions for the x's, y's, and z's that show up. If you like to have an extra arrow in here, f is a function that goes from that elliptical disk just onto the real number line. I don't have a name for the axis over here, but I'm computing output numbers from the x, y, and z. And now when I compose that with capital T, I'm computing the output numbers in terms of u's and v's, which is done by this formula. All right, so that's 2 out of 3. I've rewritten the set. I've rewritten the original integrand. I won't write the rest out. And finally, I have to change the area element. So
Could you move down the paper, please?
Oh, sorry, thank you. You know what, or push the camera forward. That should be there we go. All right, so let's get that area element. Now, to do that, the formula that I gave you last time is that we will rewrite this way of measuring areas. It will be at near each point in the UV plane. I explained to you last time why this little formula that's the area of a certain parallelogram will be the way we'll measure areas on the surface, the slanted elliptical disk. So there's an extra fudge factor here that multiplies the corresponding area downstairs in the UV plane or the XY plane. If you think about it, when you kind of pull everything upwards, then, you know, lengths have gotten longer, and so you would imagine that the areas would get enlarged as well. When you go straight up, the areas are going to be longer on the slanted thing. So what do you have to do to compute this? You need to take the partial of each of these three components with respect to u, and here's what I get: a 1, and then a 0, and then a -1/2. And likewise, the second entry here, the second vector in this cross product, will be the set of partial derivatives with respect to v. So all I'll get will be a 0, and a 1, and a -1. Now, just to pause for a second, these two vectors that I've just written down, each one of these is a column in the full derivative of capital T. Capital T is a function that's going from two-dimensional space to three-dimensional space, so its derivative at each point in the UV plane would be a 3×2 matrix, 3 rows, 2 columns. 3 rows because you have to differentiate each of x, y, and z, these formulas that give x, y, and z, and 2 columns because you need to differentiate them with respect to the 2 variables u and v. Well, there's that first column, and there's the second column. So if you take away the little times symbol in the middle, that matrix, that 3×2 matrix, that is the derivative of capital T. So I'm not asking you to compute anything you haven't already computed. These partial derivatives are just the 2 separate columns in T prime. And then you do need to compute the cross product here. It's a bit of an annoyance, but it isn't all that hard. The x component, you know that's found by taking the cross product of, it's a product of the y component here times the z component minus the z component times the y component, and that'll just turn out to be a 1/2. Likewise, for the middle component, it'll be the z component here times that x component minus this x component times that z component. And finally, the last component is that one times that one minus that one times that one, which is a 1. And so I've got, thankfully, this is just a constant vector. I can easily compute the magnitude. It's 1 squared and 1 squared is 2 1/4. So that's 9/4, and the square root of that is 3/2. Oops, sorry, times du dt. So that's the third element that has to be changed in this integral. When I switch to u and v coordinates, I know I'm integrating now over the unit disk in the UV plane. The function I'm going to be integrating is now going to have all of this plus 3uv. And now I see that there's an extra factor of a 3/2 that gets tossed in next to the du dv. At this point, I guess I would just use Fubini's theorem. I've got dv on the outside, so I would stare at that unit disk and say, oh, the v coordinates go from -1 to +1. Where's my picture? Here, this is v equals -1. Here's v equals +1. If I take any intermediate value of v and I ask about the range of the u coordinates, they go from this guy's u coordinate to that guy's u coordinate, and those numbers are the negative of the square root of 1 minus v squared and the positive, same square root. And then you have all this integrand written out with du and dv at the end. So there you go. There's 2 Calc 1 integrals that you can do. Have a good time. It's kind of an annoyance, but you could evaluate it.
Okay, thanks.
Okay, well, let me point out, though, that there's some variations that you could do here. For example, I asked you to integrate a function of 2 variables over a region in the 2 variable plane. Here I've chosen to use Fubini's theorem. You didn't have to use Fubini's theorem. You could have chosen to do this in polar coordinates. So then you would have a bunch of trig functions to integrate. Don't forget you would have an extra factor of r dr d theta. It's perfectly fine to do it that way. If you actually do something like that, if you first parameterize it and then you do a change of variables, you're actually coming up with a new parameterization, which is kind of what I was going to suggest anyway, because here is a second option you could have used on that to get that elliptical disk. You could have let x be u cosine of v, y is u sine of v, and then I still have to compute z as a function of those two. In our case, this would be z is equal to minus a half of the x thing minus the y thing. This looks like a more complicated parameterization. When I take these quantities for x, y, and z and stick them into the function that I'm supposed to integrate, I'll get a function of u and v all right, but I'll have a lot of trigonometry in that. Maybe you don't like that. On the other hand, when I ask you now what's the corresponding region in the UV plane, what are the combinations of u's and v's that you need to get exactly our elliptical disk? Well, look, this last line is already just forcing us to lie inside the relevant plane, inside this plane right here. So that's all fixed. The only other thing you need to do is to make sure that you're lying inside the cylinder, but that'll happen precisely when when u is less than 1. You'll get all the right v's by taking v going from 0 to 2 pi. So here's my region of integration now. I just have to integrate as over the rectangle in the UV plane, where u goes from 0 to 1, v goes from 0 to 2 pi. That's a lot easier than this mess, so I can jump straight to Fubini's theorem. My limits of integration would be 0 and 1, and then 0 and 2 pi. Of course, like I said, your little integrand is a little more complicated. And furthermore, your TU and TV are going to be a little bit more of a mess. When you take the partials with respect to u, you simply get cosine of v sine of v, but now you're going to have this minus a half cosine of v, plus a half cosine of v. No, I said that wrong. Minus 1/2 cosine of v minus sine of v. That's what will have to show up over here. And when you take the partial with respect to v, you got to remember your differentiation rules for the trig functions, and you'll probably get a minus sign wrong. So you could try it. You will discover that the TU cross TV is not terribly complicated. You would be able to figure out the magnitude. I can actually tell you what will happen is, in this particular case, you'll end up with exactly 3/2 times the absolute value of u. Don't forget the absolute value sign. However, in our particular case, the u's are all positive anyway, so you don't, in your integration, you don't really need the absolute value sign. So when you make all the substitutions in here, you'll be integrating over a nice rectangle. You have some trig stuff to mess with, but here at the end, your extra factors will just turn out to be a 3/2 times u du dv. So my point is, you have different options because you have different ways to parameterize the surface. Any way of computing this integral is going to force you to parameterize the surface, but you have many, many options for how to, well, infinitely many, actually, options for how to parameterize a surface. There is one thing about this example which I would like to generalize, and that is, in this example that you asked me about, the surface was actually a part of the graph of some function g. Now, this wasn't the function you were integrating, not the z squared plus 3xy. This was the minus 1/2 x minus y. Okay, so there's a function whose graph determined the surface. Or more precisely, you just wanted a portion of that surface. You wanted a portion of it that lay over some portion of the xy plane. In our case, that's where the unit disk was. So, okay, yeah, you know how you're supposed to compute an integral. You choose a parameterization t, and then you change the 3 parts. You have to figure out the combinations of u's and v's you need. You'll have to substitute your formulas for x, y, and z into the function, and then you have to rewrite the area element with this extra fudge factor. But when you're just going to be lifting the point straight up, like we did to go from the disk to the slanted elliptical disk, you can always just use that cheater's little easy parameterization. Just let x and u be the same, let y and v be the same, and then the z coordinate just has to be whatever it was, just like I did over here. That's always an option for you, available to you, if if your surface is just a part of the graph of a function g. And not only is it available to you, but it's not hard to do the calculations to get the fudge factor in here. I mean, when you differentiate these three things with respect to u, the first entry is a 1, and then you get a 0. And then you get whatever you get by differentiating that function of u with respect to u. So that's why I ended up with, when I took the t sub u, I had a 1 and a 0 and then a negative 1/2. And likewise, the other one, when you differentiate with respect to v, you get an easy 0 and then an easy 1, and then you have to actually do some differentiation. But with zeros and ones floating around in there, it turns out not to be too hard to get the cross product. I'll let you do the general case, but here's what it'll turn out to be. You'll always have a 1 in the last entry, and these other two entries, they're the negatives of the two partial derivatives of that function of two variables, whatever function that you were graphing when you made the surface in the first place. So this is a choice for a parameterization that you could use when your picture has this form. The substitution is easy. You get your new set D by just squishing downwards, go straight downwards. Those were supposed to be straight dotted lines. Sorry, they don't look too straight. But that's what D is. It's just the projection of the surface down to the XY plane. As far as your function, you're just supposed to replace every X by this, every Y by that, and every Z by that. But if X and U are synonyms, I'll just call it X instead of U. And likewise for Y and V. And then all you're doing really is replacing Z, every occurrence of the letter Z, with the combination of X's and Y's that it takes to get the Z. Well, that part's easy. And then the differential is, the fudge factor in front of the differential is just supposed to be the magnitude of this vector. That's the sum of the squares of those three components, square root of that. So it's a square root of 1 plus, and you take the partial of this function with respect to x and the partial with respect to y, square them both, add them up, add 1, take a square root, there's your fudge factor. So this is a very general situation. You could do this for many of the examples that we ask you to do. Many of the kinds of integration problems that we ask you to do, the surface in question is just part of the graph of some function of two variables. Now that won't apply to the sphere, for example. If the surface in question is a sphere, that's not the graph of a function of two variables because it fails the vertical line test. Every vertical line will pierce the sphere twice, not once. But a hemisphere, you could think of that as the graph of a function, the graph of a function of two variables, or the lower half. So keep that in mind as an option. I want to say one more thing about surface integrals before I turn to this new thing called line integrals, which is, let me just show you that, you know, sometimes sorry, I crossed things out, I shouldn't have done that. Sometimes it happens that the surface that you have to integrate over happens to be just down there in the XY plane. There's no reason when I say it's a floating surface, it doesn't literally have to float above the XY plane. There's no reason that they can't all have a 0 as their Z coordinate. Now, if you had that, of course, you could use this recipe that I was just talking about where U would be, X is U and Y is V and G is just 0. And that's fine, but that doesn't necessarily make your life easy. But you still have the option of parameterizing this by something else. Like if you saw a quarter disk in the XY plane, you might say, why don't I use the polar coordinates kind of formula? And that would take you from a rectangle in the UV plane into your quarter disk in the XY plane. So choose a different parameterization over whatever region, whether it's a rectangle or not. Parameterize this surface. If it's supposed to be down on the floor, then the Z coordinate has to be a 0, but I don't really care what you use as your parameterization for the X and Y coordinates. Pick any formulas you like. Of course, you'll have to figure out what the set capital D is over in the UV plane, and that could be tricky if you're kind of wild in your choice of the two components of capital T. But as far as the other part of your calculation goes, where you need to mess around with the area element, the dA, and you need that magnitude of a cross product, look what you're going to do. Sure, you're going to compute partial derivatives with respect to u and v of both of those things, But when you go to compute the partial derivatives of the third component, if that's always a 0, you'll have 2 zeros here. And now when you take the cross product of those two vectors, well, among other things, these are two vectors in the UV plane, and the cross product of them has to be perpendicular to both of those vectors. So it has to point straight up. It'll have zeros for its first two components. Only the last component survives, and that'll turn out to be this times this minus this times this. So when I ask you for the absolute, the magnitude of that cross product, all you're going to get will be the absolute value of this expression, which I hope you realize is the determinant of the derivative of capital T. There's the two partial derivatives of both T1 and T2 with respect to both U and V. And you're taking the determinant of that 2 by 2 matrix. So for those of you who are asking, why is the determinant of the Jacobian involved in the change of variable formula? It's because the change of variable formula is exactly this special case of how we compute a surface integral. In the special case where the surface is down there in the xy plane in the first place, your change of variable amounts to just a way of parameterizing such a flat surface. And it will then, by the general formula, you'll see that you'll be stuck with this determinant of the Jacobian matrix. So if you like, as you prepare for the test, you can throw away the whole chapter on the change of variable theorem and say, oh yeah, well that's just for how to evaluate surface integrals. All right, I don't really recommend that you forget the change of variable chapter, but it's something you can try. All right, so other comments or questions that you have about computing surface integrals? They all begin with that parameterization. Yeah, Youngju, go ahead.
Yes, so just for curiosity, we talk about path integral, we talk about surface integral. What happens if we have like 4 variable in the first place? Like, can we parameterize them by 3 parameters? And how do we do next? How do you proceed?
Yes, that's a very good question. So actually, let me take your question and put it into the context that I was about to describe anyway. Look, we've been doing these path integrals where somebody gives you a function defined on this curve that wanders through 2 or 3 dimensional space. And I have told you how you can compute these in a very natural way. Once you realize what it is you're trying to compute, you realize that an easy first step is you got to parameterize the path. You write x and y as functions of your parameter. If you're in 3-dimensional space, also give z as a function of that parameter. And if you're in 4-dimensional space, why not give the fourth coordinate capital little w as a fourth function of t? And then you'll take those formulas for x, y, z, and w and shove them into the function of 4 variables. You'll need to evaluate that function over some region in the t line now. But what you find out the range of t's that you need, and those will become your limits of integration on this integral. Of course, you'll need to multiply by the length of such an arc in 2 or 3 or 4-dimensional space, but always that's given by the distance formula. It's always going to be the magnitude of this derivative of phi. Actually, if you think about phi as specifying your position in space at time t, then phi prime, the derivative, is your velocity. The magnitude of that is your speed. And if you multiply speed times dt, a little increment of time, speed times time gives you distance, which is what you wanted to put here. So I have these 2 formulas here because I've been using the letter capital L to say that when we partition this, we multiply values of the function times the size of a piece, and size should be length. So I've been using capital L to tell you about length. You may have noticed in the book they use a little s. I have no idea why, but that is their choice of how to indicate that you'll be measuring sizes by length. Now, after you talk about path integrals, there's 2 ways that you can go. The book next talks about line integrals, which are things that involve vector fields as well. I'm choosing to postpone that for right now, and I'll talk about it in just a few minutes. So where I would rather go next is to say, let's use the same idea, but up the dimension by 1. Instead of having 1-dimensional things, which are curves, let's talk about two-dimensional things, which are surfaces. The idea behind what an integral means is still the same. You need to talk about how do you want to take this surface and chop it up into little bits. You evaluate this function on each one of those little bits, and you multiply by the area of the little bit. As we saw earlier, the book chooses to write ds, capital S, instead of dA. I don't know why, but that is actually not uncommon. So these are two different notations for the same thing, but the spirit of it is still chop up, evaluate, multiply by an area, add them up, take a limit. The practical way to evaluate this is to parameterize the surface. If it's a two-dimensional surface, you'll need two parameters. Express the x and y, maybe just two, or x, y, and z coordinates, or even x, y, z, and w coordinates as functions of just the two parameters u and v. And then you'll do the same thing that we did before. You'll say, well, this surface corresponds to just a certain chunk of UV space. So you'll write this as an integral over that chunk of UV space. So should I put down that that's a subset of the plane? You'll have to evaluate the function in terms of u's and v's, but that just means substitute in what x and y and z and w are. And then you need to put in something that measures how much the area has changed when you mapped this chunk of two-dimensional space into three-dimensional space. And that's where I've been asking you guys to compute TU cross TV. Now, this is the one part of the formula that would have to change a little bit if you happen to be computing a dimension, an integral over a surface that's in four-dimensional space, because then you don't have a cross product anymore. There's no cross products in four-dimensional space. But if you remember where this came from, it was still just asking for the area of a parallelogram that had TU and TV as the vectors along the edge. So I can use a similar phrasing of what I would need to do in the four-dimensional setting. You just need to know how to compute the area of a parallelogram, two-dimensional parallelogram, that's floating around in a four-dimensional space. And as you might imagine, the calculation can be done just knowing those two vectors. So there's a similar formula for how to do this. You take the two vectors in R4, and instead of just taking a cross product, there's a way of you play around with all the different possible determinants involving pairs of coordinates in the two different vectors. By the way, since you asked about higher dimensional spaces, you could continue the dotted lines if all of this was about one-dimensional integrals over a one-dimensional thing like a curve, and then a two-dimensional thing like a surface. You could also ask about integrals over three-dimensional objects that float in four-dimensional space. It comes out to basically the same thing. You need to discuss how volumes are shifted under a parameterization. And I'll just say that it is something that involves a lot of determinants of 3x3 matrices. But it's now time for us to throw in vector fields. And everything that I'm going to say about vector fields and curves has a corresponding thing involving vector fields and surfaces, but that's going to show up after the exam. Okay, you're not going to be responsible for that for the test. Let me show you why vector fields show up in a setting of doing integrals over a path. So here's the issue. Suppose that you're walking, and this can be, I have it along a real number line here, but imagine you're walking in any direction along any curve in space. And as you walk, you feel a wind coming in at your face. So there's some force that's blowing. Then you know that the work that you have to do is equal to the force that you feel times the distance that you travel. And in particular, the work that you have to do per unit foot of travel is just measured by this force. The problem is that force is usually a vector. That's what our vector fields are. Remember, we had little pictures that show the wind blowing all over the plane. And what I need in here is not the size of that force, because if the wind is just blowing, even if it's a strong wind, if it's blowing straight down, it doesn't make my work any harder. It just gives me a headache. In fact, if the wind is blowing on this side, it actually gives me a push and I do less work. The way that you actually calculate the work is that you, or more precisely, the work per unit distance, is you need to take this force vector and you take the magnitude of that, but you reduce it by the cosine of the angle that's between the direction in which the thing is coming in and your direction of motion. So you need to multiply by the cosine of these two angles, which would be given by, you take a unit vector, take a unit vector in the direction of your travel and take the dot product of F with that unit vector. Now, if you're moving along a curve, that unit vector will actually be a tangent vector, the unit tangent vector along the curve, right? If you're moving like this, and if I stop you right here and ask you about your velocity is tangent to the curve. So I'll multiply that by u, and I got to stress, I just want the unit vector. You know that in general, when you compute the cross product, you get the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. And I don't want that magnitude to show up, so that's why I insist on a unit vector. You could take your velocity vector, because that would also be tangent to the curve, but it might not be a unit vector. So what you would do is take your velocity vector divided by the magnitude of the velocity vector. And then this would represent the amount of work that you have to do to fight this force. And I realize now that I should say I'm off by a minus sign. This is the work that's done on you by the force. If I actually want to talk about the work that you do, that would be force times distance. So it'll be actually the negative of this. Right? If the force is blowing that way and you're trying to walk that way, then the dot product would be high, but that's not, you don't have to do much work. You do a lot of work if you're going that way and the force is going this way, and then that's a positive amount of work that you're doing, but the angle theta in that case would be 180. So this would be a negative one. So this is the way the signs have to work. All right, the point I'm trying to make is the amount of work that you have to do per unit foot or unit meter or whatever, that's a number. It's not a vector, it's a number. And what you will do to calculate the total amount of work needed to move from this point to that point is the same kind of story I've talked about before. Figure out how much work it takes to get from here to here, add to how much work it takes to go from here to here, and so on down the line. And every one of those amounts of work that you do to move from one point to the next is found by measuring exactly this kind of a quantity. That's the work that you do per unit length, and you multiply it by how far you moved, which is the length of this arc. So this becomes a very natural way of computing work, the total amount of work that has to be done, as an integral. You're going to integrate along whatever path somebody asks you to move on, and you're going to integrate a function with respect to length, a numerical valued function, no vectors in here, a scalar valued function. And precisely what it is it's the negative of the dot product of this force vector field dotted with this, this is a unit vector that points in the direction that you're moving. And as I say, one way to compute it is to take your velocity vector and divide by the length of that velocity vector. Now, I know I'm at the end of my hour, but I gotta show you, because this is just way cool. How would you compute this path integral? Our first step is always you have to parameterize the path. Well, I've sort of already been talking about that when I referred to your velocity. I must have been moving along the path. So I had a position at all times t. So I already had a parameterization in mind. And so I would think about this as the t's ranging over some interval. And then what would I have to do? I have to take this function, little f, and you know I'm supposed to just take the composite with phi. In other words, stick in x of t, y of t, and z of t. And then I'll multiply by this magnitude of phi prime over here. And that's what I integrate with respect to t, right? So there's a bunch of stuff I'm supposed to write in here, capital F of phi of t, and then I have my velocity at time t divided by the magnitude of my velocity. But here is the gift from nature. Your velocity is exactly the derivative of your position. I got different notations here, but these two things are asking for exactly the same thing, so you get some cancellation. You don't have to worry about that. You just are going to integrate, you evaluate the vector field at the position that you're standing at, and you take the dot product of that with your velocity, which is the phi prime of t multiplying dt. So no magnitudes, it's just completely gone. You still have to do the substitution part. You still have to compute the velocity, but it's the dot product of your velocity vector with this force field at each moment in time. Okay, so I'm going to have to defer this to Wednesday to actually do the calculations. And I do want to stress you'll see a lot of different notations for these things. But in spirit, you are just computing the kind of path integral that we've been computing, where the scalar valued function little f involved is actually computed by some kind of sophisticated dot product that takes into account a vector field that represents a force that you're fighting. Okay, so the fact that it's a special case like that leads us to a special formula that's a little easier to compute, to evaluate numerically. You don't have to take advantage of that little gift from nature, it's fine. But if I were you, I wouldn't pass up a gift. So I went over a few minutes. I can see we do have a lot of work to do here, but do you have a quick question you want to ask me before we depart? Ooh, I see the chat box has been pretty empty. It's been pretty full, rather. Move paper up, yeah, okay. All right. Oh, yes. At some point, Zhang Yu was reminding us of a formula for the area of a parallelogram, and that is correct. You can take the product of the two lengths times the area, the sine of the angle between them. Of course, computing the angle is a bit of a nuisance, but yes. Yangzhou, you have another question. I see your hand up.
Yes. So the difference between what we learned about in this chapter and the previous chapter is that in previous chapter we have 3 parameters for 3 variables, and in here we only have like 2 parameters for 3, or like 1 for 2.
Correct. Correct. So as I showed you with this this picture here, the previous one was actually, the previous chapter was sort of just a special case where the number of parameters matches the number of the dimension of the space that everything lives in. And now we have, like, as you say, 1 parameter in a 3-dimensional space or in a 2-dimensional space, or 2 parameters in a 3-dimensional space. So this number is always lower than that one. Yes, that is the difference.
Okay, thanks.
All right, guys, let me switch now to office hours. I'll be happy to continue this conversation if you like for an hour, and then I will be back for another hour at 3. Take care and stay healthy, and then I'll see you again on Wednesday.